My name's Steve Regan and I'm a computer science teacher. Today I'm going to show you half adders and full adders. That is theory to actually building circuits practically. So we'll start off with half adders. If you look at your course book, you will have already understood this in your second year. And we look at XOR gates and AND gates linked together so that they have a 2-bit input, which can be a 1 or a 0, 0, 1, or a 1 and a 1, or even a 0 and a 0. And they have some sort of output and a carry. So if we look at this, we can see the truth table for an XOR gate is if you have a 0 and a 0, you get an output which is a 0. Or a 1 and a 0, and you get an output that is a 1. And likewise, a 0 and a 1, you get an output that's 1. But if you get two outputs that are 1, you get a 0. You look at the AND gate here, and that's fairly standard. So you get a 0, 0, and you get a 0. You get a 1 and a 0 input. You get a 0. You get a 0 and a 1 input, and you get a 0. And you only get an output if you have a logical 1 and a 1, and then you get an output of a 1. So let's have a look at an actual chip here. These are the IC chips I'm going to be using, and they're made up of a power input and a ground, and you also have here a little indicator which tells you which way to put the chip round on the board. And inside that you have 4 XOR gates. So there's your input A, input B, and there's your output, and so on for the 4 gates. You've also got a 4 logic gate and chip here. Same sort of configuration, except the outputs are in a slightly different place here. You've got your power, you've got your ground, you've got your input A, your input B, and you've got your output, and the same here, here and here. So as you can see, you can configure these together in this sort of configuration on a sort of breadboard, and you get this output. So if a half adder, if you've got a 0 and a 0, you will have your S, that's your actual LED output is 0. If you've got a 0 and a 1, your LED output will be a 1. And if you've got a 1 and a 0, your LED output will be a 1. And if you get a 1 and a 1, your LED output will be a 0 and a carry 1. So that equates to a mathematical equation of having one bit which you can add together, one on top of the other. And if it's a 1 and a 1, obviously it's going to be a 0 and a carry 1, which is 2. And that's that bottom line here. And this is the algebra for the gates above there. You can see that S, that's the LED output we're going to do, equals A input or XOR B input, and the carry is dealt with by the A and B inputs. Okay, so there's the actual circuit itself, which I will show you the build of later. So there's your chips configured together. There's your power inputs. There's your ground input. That's your you're actually grounding. So you make the circuit, and you can see that you can pause the video and see how this all works. You can see your various inputs here using the bottom half of the chip so that we get this configuration over here on the right. I'll let you pause and ponder that video later. So in order to get a full mathematical circuit here, we have to have a full adder, okay? And basically here, we've got an extra gate. So we've got 2 circuits here, and we've got two half adders put together with an OR gate. So that's two half adders put together with an OR gate. And what that does then is that it takes the carry circuit and places that into the AND and the OR, and basically it sort of gives you a full carry here. So basically what we have is a carry to consider when it goes forward. So the extra gate we've got here is an OR gate, and here's an OR chip here. So a 0 and a 0 is a 0, a 1 and a 0 is a 1, and a 0 and a 1 is a 1, and a 1 and a 1 is a 1. And there's the other two gates that we've used there. And here's the actual gate configuration. Okay, so there is a full adder here. Basically, I'll just go back one and just show you the truth table for that. So these are the inputs here for the carry bits, and these are the A and B. So that is feeding back a carry into the two circuits to give you the carry to pass forward. And that will give you a truth table, which is very similar. So 0 and 0 is a LED 0, a 0 and 1 is a LED 1, 1 and a 0 is an LED 1, a 1 and a 1 is an LED 0 and a carry 1, and we can put that as a sort of LED output as well. And we've got a 0 and 0 and a 1 and a 0, and we've got a 0 and 1 and so on until we get a 1 and a 1, and you've got the carry bits here. Look, so that's a 1 and carried 1, that's a 1 forward. So as long as that feeds back in, so this is this one feeding back in, and we've got a carry 1, a 0 and an input 1, and that gives us a carry 1, and that's the same as a 2. And then we've got a 1 and an input from the 1, which gives us a 1 and a carry 1, and then we've got a 1 input and a 1 and a 1 with the two input switches, and that gives us a 1 carry 1. Okay, so there's the implication of the full or implementation of the algebra here for a full adder. So we've got an A or B or input C, which gives you the output here on the LED. And then we've got the output C's configuration here. That's the output C's, and that is from the input, which is X up here, but that's the input C, A and B, or A or X or B, and C. So those basically are the ANDing of these, the XORing of these, and the input from here. So basically that gives you that, and there's the key at the bottom for the different gates. So what if you look at that logically, that gives you a full 1-bit circuit, which allows you the 1 carry 1 at the end. Okay. So now we move on to actually putting a full adder in, implementing a full adder. So we've got an XOR gate, an AND gate, and an OR gate, which we string together. And you can pause the video to look at this, and you can see the logic of it all being put together. So that's okay, because that gives you a 1-bit system with a carry, and you can mimic there an equation by putting 2 LED lights in, and if you configure them right, you can have the S on the right and an input of a, so in fact what we can do is put, oops, let me go back one. So we could put an LED light on here, so we can have the S here, and we can have the carry LED here. And what I've got is a little setup with an LED there and an LED there. So using that truth table before, if we have a output, if we have an input of a 1 and a 1 and a 1, remember that is carry in there. Then we've got, and I'll just put them out there. And what that will do is it will turn that on and that on. Because what we have is an equation where we have this, which is a 1 and a 1 and a carry 1, which is leaving 1 behind and taking 1 forward, which is a 1. Okay, so that's straightforward basically on that. So now what I did was, and this looks really complicated, I've actually done it so that I can have a two switch input here, a 2-bit input. So if you look at this mathematics down here in the bottom center, I can add 1 and 1, which is 3, and 1 and 0, which is 2, and I could come up with the answer as 5. And I've used the sort of carry bit. So I've extended it with 2 full adders, and it drops out a carry. And that works by having your 2 full adders here, but they're joined together because the carry from this one here, the second adder, feeds back in to the first adder there. Okay, so you get a carry in, and we have a blank adder. So that means that you get your 2 sums, and you get your carry LED here. So you can have a configuration where I can sort of, if I just draw this here, I can put a 3 banked LED here. Well, forgive my drawing, 2 and 3, and basically, if I had 2 banks of switches, and I turned 1 bit the first 2 switches on, and left the second one off and on, what I'd get is a configuration where that would be on, that would be off LED, and that would be on. Just like that configuration down here. And I could get the 6 here by turning all of these on here, there. And that would then give me a configuration where this LED was off, that was on, and that was on. How would that transpire? Because that is 1, 2, and 4. So 4 and 2 and 0 in this case equals 6. This one here, which is 4, no 2s and 1, which is 5. So that's how it would work basically. So what I'm going to do now is I'm going to record another video and splice it onto the end here, so that you can see my 2-bit full adder circuit in action. So this is my circuit here, and basically what I've got is configuration of logic gates. I have a AND gate here, as we saw on the diagram and the representation diagrammatically of the chip. We've got an XOR gate and an OR gate, and they're all wired up to 2 inputs. Now this could constitute the top row, and this could constitute the bottom row of any equation. So for example, I'm only using the first two inputs here because this is two full adders strung together, and the output's going to be put onto these LEDs here. So I'm going to use the two outputs here plus a carry to give the illusion of a third output. So basically what we would do is, if we wanted to put two numbers on there, say a 1 and a 1, and we wanted to put a output on there, a 0 and a 1, then what we would do is we'd have a 1 and a 1, which is 0 carry 1, and then a 1 and a 1, which is 0 carry 1, which would give us the answer 4. So how do we work that out? So we put that on top there like that, and we'd have a 2 and a 1 in binary is 3, plus a 1. And remember, we're adding because it's a adder. There's two full adders there, and that would give us that. So let's actually do that. So we're going to put the top row onto there. We've got I'll just use a pencil because it's a bit better. So we've got the 1, 2, there's your 3 plus a 1, and lo and behold, there is your 4. So we can do any number of these equations here. We've got your inputs down here and we've got the actual LED outputs here. And I've done it the right way round, so you can see that this one corresponds to this row here. This output corresponds to this row here. So that's the 1s and the powers of 2. And the carry bit, which is on at the moment, is this one here. So basically what we have is a configuration in this chart here. And this one we're doing at the moment is a 1 and 1 in this input here, and we have a 0 and a 1 in that output here. So the answer would be a 0 in the first LED, a 0 in the second LED, and 1 in the third LED. So again, what I can do is do any one of these equations. Let's take this one here. If I put a 1 and a 1, and we're going to make up a 5. So let's look at a 5 configuration. So we've got a 2 and a 2, which should give us 4. Okay, so basically we've got a 4, and then we could add 1 on any one side there, and that would give us a 5. So a 2, and a 1 gives us 5 on that side there. Okay, so basically we can do that, and we can do the bottom one if we turn them all on. So we've got a 1 and a 1, that's a 3 plus a 3. So mathematically this would look like this. So we've got a 3 plus a 3. Remember, that's a 1 and a 2, so that equals a 3, and that equals a 3. Then what it literally equates to is a 1 and 1 is 0 carry 1. But we've got a 0 carry 1, and we've got a 1 and a 1, which leaves 1 behind and carries 1. So we have a 6. So that is the circuitry for a 2 full adders placed together, where the carry is fed into the second adder. The first carries are grounded here, so that means that they are earthed, and then we have the circuitry all built up here with 2 inputs, which equates to the numbers on the top and the bottom of the equation, and we've got the outputs. Now I've put another AND gate and a XOR gate on the top here because I'm going to add it up to a 4-bit circuit, and obviously that would mean that I would have to add another adder, couple of adders on that, which would eventually make it up. So you'd get four full adders to make a 4-bit circuit. And of course, if you wanted an 8-bit, then you would have to add the corresponding chips to that. Each one has a number of adders. The reason why I'm not going to add another OR gate is because if you go back to the original diagram, you would only have another OR put onto that. So if I grab the diagram here again and show you, you've got 2 OR gates. So one chip at the moment is feeding just one circuit, and then I would just add another one. I would not need to add another one to go up to 4 bits, but I would have to add another chip if I wanted an 8-bit circuit. So basically that is the circuit you would need for 2 full adders, and possibly in the future a 4-bit, that's 4 adders. Thank you for watching.